Hello. We are going to do some more chain rule today, but with transcendental functions and kind of enhance some of the rules that we already have about derivatives. So what we are actually going to start with, ignore the bell, is we are going to start with the derivative rules for trig, and then exponential and logarithmic. Now, we've already talked about trig, and we did that in the first lesson. And we said when you do the chain rule, in layman's terms, it's the derivative of the outside, keep the inside, times the derivative of the inside. And so like if I were to take the derivative of sine of f of x, where f of x is like an inner function, the derivative of the outside would be sine, keep the inside, sine of f of x, times the derivative of the inside, times f prime. And so I like to use that function notation to show how the chain rule works when you're dealing with trig, exponentials, and logs. So if I come over here and say, well, what about e? Well, we had learned before that the derivative of e to the x is e to the x, but what if it's not just x? What if it's e to the 2x or e to the x squared or something like that? Well, the rule just becomes a chain rule. The derivative of e to the x is itself. The derivative of e to the f of x is still itself times the derivative of the exponent. Now, how does that jive with derivative of the outside, keep the inside, times the derivative of the inside? We kind of think of it that way as the derivative of the outside is like the derivative of e to the something is itself. So there's like the derivative of the outside, keep the inside. And then we consider the inside that exponent, and so there's the times the derivative of the inside. And then when it comes to ln, the derivative of ln x is 1 over x. But what if I don't have ln x, ln 2x, ln x squared plus 7, something like that? Well, if you want to take the ln of f of x, it ends up being the derivative of f of x over f of x. And what you'll often hear me say out loud is I shorten this to the derivative of the end over the end. That's what I'll often say for the derivative of ln functions, the derivative of the end over the end. Again, how does this jive with derivative of the outside, keep the inside, blah, blah, blah? Well, the derivative of ln x is 1 over x. So the derivative of the outside is 1 over f of x. Keep the inside. Then times the derivative of the inside is times f prime of x. You can think about this as 1 over f of x times f prime of x. Derivative of the outside, keep the inside, times the derivative of the inside. Now, I've really just rambled a whole bunch right now. I just need you to memorize these. The derivative of an exponential is itself times the derivative of the exponent. The derivative of an ln is the derivative of the end over the end. And now we just use it. So like right here, it says find m prime if m of x is 3 times tan squared 5x. Okay, so that's one of the trig rules. Yeah, but I have a trig rule and tangent is squared, so we have to do a double chain rule here. Here's what that means. I'm going to rewrite m of x as 3 times the tangent of 5x squared, because that's really what tan squared 5x means. So if I want to find m prime, the 3 is going to stay because it's a coefficient, and now I'm going to do the derivative of the outside. Well, the outermost thing that's happening is squaring, so I'm going to bring down the power and reduce it by 1. So there's the derivative of the outside, keep the inside. Now, times the derivative of the inside. I need times the derivative of tan 5x. The derivative of tan is secant squared. Keep the inside. Times the derivative of the inside. It is a double chain rule. I took the derivative of the squared, and then the derivative of the tan, and then the derivative of 5x. So m prime is 3 times 2 times 5, that's 30. Tan 5x times secant squared 5x. Okay. The next one says, all right, let's go back and find tangent lines. Find an equation of the line tangent. Tangent lines, x, y slope. Find the equation of the line tangent to g of x at x equals 1. All right, so if I need a tangent line, x, y slope, x is 1, y is what I get when I plug 1 into the original, and that's going to be 6e to the 4th. My slope comes from the derivative. Okay, so I need g prime of x. Well, this is 6x times e to the 4x, so I have to do a product rule. The first times the derivative of the second. The derivative of e to the 4x is itself times the derivative of the exponent. So there's the first times the derivative of the second plus the second times the derivative of the first. Evaluate that at 1, and I get 6 times e to the 4th times 4 plus e to the 4th times 6, which is 24 e to the 4th plus 6 e to the 4th. That's 30 e to the 4th. Woo! Okay, and now I have a tangent line. Y minus y1 equals m x minus x1. That's it. It's okay to have e's as your m's. It's okay to have e's as your y value, no problem. And there's a tangent line. Number 3 says write an expression for f prime if f is h of ln of 2x. Just another chain rule. I've got an inside function, I got some outside functions, I'm just going to roll with it. So if I want f prime, I'm going to take the derivative of the outside, keep the inside, times the derivative of the inside. The derivative of ln 2x is that new derivative of ln's, which is the derivative of the end over the end. So the derivative of ln 2x is the derivative of 2x, 2, over 2x. Derivative of the end over the end. So f prime of x is h prime of ln 2x times 1 over x. That's it. Okay. Now, there is more, so turn the page. We now are going to also need to know the derivatives of exponential and logarithmic things that aren't base e. So instead of e to the x, what if you had 4 to the x or 9 to the x? If you want to take the derivative of a to the f of x, okay, where a is any number, including e, the derivative of a to the f of x is still itself times the derivative of the exponent, but then also times the ln of the base. Okay, so what would that mean? That would mean if I was doing like the derivative of 4 to the 3x, it would be itself times the derivative of the exponent times the ln of 4. Okay, I'll deal with y in a minute. And if you're dealing with logs, log base b of f of x is still the derivative of the end over the end, but also now we have over the ln of the base. So instead of times the ln of the base, we're dividing by the ln of the base. And an example of that one would be like if I wanted d dx of log base 5 of 6x plus 1. The derivative of any logarithm is the derivative of the end over the end. And then also in the denominator, I have to multiply by the ln of the base. So that would be times ln 5 on the bottom. And we just leave it like that. That's what it is. That's how you take the derivative. Now, I need to come back and do some exponents and log review for you because some of these things you either may have forgotten or didn't know in the first place, and you need to know them. So, some quick review. ln of 1 is 0. ln of e to the 4th is 4. Now, how come? It's because when you type the ln button into your calculator reads that as e to what power is So when you type ln1 into your calculator, you're asking your calculator, e raised to what power is going to be 1? Well, the 0 power. When you type ln of e to the 4th into your calculator, you're asking your calculator, e to what power becomes e to the 4th? Well, it better be the 4th power, okay? And that leads to a not always true, but mostly true, little shortcut. If ln and e are touching, they usually cancel each other out, okay? That doesn't happen every time, but it happens most times, all right? E to the 0, that's going to be 1. E to the ln, I think on your paper this says 6. E to the ln 6 is 6, okay? E to the 0 is 1 because anything raised to the 0 is going to be 1. Except for 0, that's undefined, we'll get there later. But any non-zero number raised to the 0 is 1. And then e to the ln 6 equals 6 for 2 reasons. 1, that cheap trick of if e and ln are touching, they can cancel. But also, a better reason, when I type e to the ln 6 into the calculator, ln 6 means e to what power equals 6. And then your calculator spits out a number. And then you know what you do? You raise e to that power. So if ln 6 means what power can you raise e to get 6? And then you raise e to that power, you better get 6, okay? Then down here we have log base 4 of 16. That means 4 to what power is 16? 2. F, log base 30 of 5 plus log base 30 of 6. I don't know what log base 30 of 5 is. I also don't know what log base 30 of 6 is, but you know what I do know? I do know if you are adding logs of the same base, you can multiply what you're taking the log of. So log base 30 of 5 plus log base 30 of 6 is the same as log base 30 of 5 times 6, which is 30. 30 to what power is 30? The first power. So that's just to remind you of some log laws. And then down here we have log base 5 of 27. I don't know what that is. I know that it's something like 2.1, 2.2, because 5 to what power is 27? Well, 5 squared is 25, so slightly bigger than 2. But here's what I want to do with this one. You need to know something called the change of base rule. Log base 5 of 27 is exactly the same as log base 10 of 27 over log base 10 of 5. Is exactly the same as ln 27 divided by ln 5 is exactly the same as log base 2 of 27 divided by log base 2 of 5. Okay. Now, I am not saying that log base 10 of 27 is equal to ln 27. I'm not saying that. I'm saying if you divide these, you get the same number as if you divided those, as if you divided those, as if you typed in log base 5 of 27. And I just want to show you real quick on Desmos. So if I did log base 5 of 27, it's 2.047. Okay, cool. If I did ln 27 divided by ln 5, I get that same number again. If I did log base 10 of 27, there we go, divided by log base 10 of 5, hey look, it's that same number again. Those are all equivalent. Now, this is the one that seems like, wait a minute, what? Let me show you where that comes from. All right. I'm just going to come over here and show you. So let's say I had 5 to the x is 27, solve for x. There's a couple ways to do that. You were taught 5 to the x is 27 converts into log form, where the base of the exponent becomes the base of the log. The number goes here, and there's an x on the other side, and you're done. That's exactly right. But here's the thing, log base 5 is garbage. Nobody uses log base 5. Well, maybe that's not true, but very few people use log base 5. In the real world, we use log base 10 or log base e, aka ln. Nobody uses these other crappy bases. So there's another way to solve this equation. 5 to the x equals 27. I can, if I choose to, take the ln of both sides. Okay? The biggest power move in all of mathematics is that you can do whatever the heck you want as long as it's an equation and you do it to both sides. It's great. It's great. I could do it whenever I want. I could have taken both sides here and raised them both to the pi power. Now, I'm not going to do that because it's ridiculous, but I could. So what I'm going to do is I'm going to take the ln of both sides. Why? Because now I can use the shooting star rule for logarithms that says if you are taking the log of something raised to a power, that power can come down in front. I call it shooting star. So this can become x ln 5 equals ln 27. And then if I want to solve for x, I can divide by ln 5 and get x equals ln 27 divided by ln 5. Well, if you remember, what I erased before this is that we had written this in log form like that. X equals log base 5 of 27. X equals ln 27 over ln 5. They're the same thing. Okay? All right. So just know the change of base rule. I'll explain why that's important in a little bit. And then the next part says rewrite 5 to the x as an exponential with a base of e. Okay? Interesting. So if I want to write 5 to the x as an exponential with base e, I can do that like this. E to the ln 5 to the x. Crazy, right? What I'm basically doing is I'm saying 5 can be written as e to the ln 5 because of that rule where like e and ln, if they touch, they can kind of cancel out. So I can rewrite 5 as e to the ln 5 raised to the x. And then I can say, all right, that's the same as e to the ln 5 times x. Yes, because power to a power multiply the exponents. Now, why do I care? It's because let's say I wanted to take the derivative of 5 to the x. Well, I just told you that the derivative of a number raised to the x is going to be itself times the derivative of the exponent times the ln of the base. That ln comes from right here. d dx of 5 to the x would be the same as d dx of e to the ln 5 times x. Well, the derivative of e to the something is itself times the derivative of the exponent. The derivative of ln 5 times x is ln 5, because ln 5 would like act like a coefficient. And then e to the ln 5 times x is really just 5 to the x. And that's where the rule comes from. Really quick, I'm almost done. Rewrite log of x. Oh, I messed up my computer. Rewrite log of x as a natural log. This is log base 10 of x, which can be rewritten as ln x over ln 10 using that change of base rule. And that's what creates the log derivative that has an ln on the bottom, because here's that extra ln on the bottom. The derivatives. Take 3 seconds to take these derivatives. dy dx. Well, I have an exponential. I have a number raised to an x. So the derivative of an exponential is itself times the derivative of the exponent times the ln of the base. There it is. That's the derivative. You can't do anything else with it. You just leave it. You can do other things, but we're not going to. Mrs. Weber, what can we do? I can re-shooting star this and rewrite this as 3 to the 2x minus 1 times ln 9 if I'm feeling fancy. But you don't have to. And then over here, log base 5 of this, if I want to take the derivative of a logarithm, it's the derivative of the end, 6x minus 6, over the end, the derivative of the end over the end, times the ln of the base. I could factor out a GCF here, but I don't feel like it, so I'm going to leave that as is. All right, now I'm done. Have a good rest of your day, and I will see you in class.